Welcome back. Today I'd like to talk about the Poisson probability distribution. Last class we learned, how can you tell if a random variable x is a binomial random variable? And today, how can you tell if a random variable x is a Poisson random variable? Okay, let's take a look. Objectives. We want to be able to determine whether a probability experiment follows the Poisson process, as I said. We want to be able to compute probabilities of a Poisson random variable. And we want to be able to find the mean and standard deviation of a Poisson random variable. And let's start with the first objective. Determine if the experiment follows a Poisson process. Well, we have to know what that means. So a random variable x, the number of successes in a fixed interval, follows, and by the way, I'll underline that. The number of successes in a fixed interval, so we have to be told whatever that fixed interval is, as you'll see in a moment, follows a Poisson process if the following conditions are met. The probability of 2 or more successes in any sufficiently small subinterval is 0. The probability of success is the same for any 2 intervals of equal length, and the number of successes in any interval is independent of the number of successes in any other interval, provided the intervals are not overlapping. Okay, let's start with the problem. So the FDA sets a food defect action level, FDAL, for various foreign substances that inevitably end up in the food that we eat and drink, and the liquids that we drink. For example, the FDAL level for insect filth in chocolate, kind of a gross question, is 0.6 insect fragments per 1 gram. So the first thing I do when I read these kind of problems is I write important information. 0.6, I'm just going to write insect fragments per, I always look out for the word per 1 gram. See right there when it's telling me per some interval, what happens per some interval, I'm thinking Poisson process. But let's keep reading. Compute probabilities of a Poisson random variable. We have to know the formula for starters. If x is the number of successes in an interval of fixed length t, now t doesn't necessarily have to be time, it's just some interval of fixed length. Then the probability of obtaining x successes in the interval is given by this notation. Don't get scared of the Greek letter lambda. So we've got lambda t to the x over x factorial, and then we've got e to the negative lambda t. I do want to mention, and I'm going to write on here, I prefer, if you have to sort of memorize a formula, I prefer mu to the x over x factorial, e to the negative mu. So for p of x, I prefer basically this formula. And you might say, well, why? Because mu, as we're going to see in a moment, is equal to lambda t. So basically, if you know mu, which is lambda t, you can view. I think it's easier to memorize that formula, basically, than this one. Kills 2 birds with 1 stone. So where lambda, the Greek letter lambda, represents the average number, I keep reading here for you, represents the average number of occurrences of the event in some interval of length 1, and e is, of course, the transcendental number 2.718. It's a mathematical constant. Okay, well, let's take a look. I know that formula can seem daunting. Okay, so here we're back to that insect larva problem. So we've got 0.6 insect fragments per 1 gram. That's what the FDAL level for insect filth in chocolate is found for this example. Suppose that a chocolate bar has 0.6 insect fragments per gram. Compute the probability that the number of insect fragments in a 10-gram sample of chocolate is. So what I do, for starters, let me write on here, is I think about mu. Well, mu is equal to lambda t. And lambda is this rate that you have. Be on the lookout for the word per. So in general, that we know that the FDAL level for insect filth in chocolate is given as 0.6. So it's 0.6, and I'm just going to write here infrag per 1 gram. But the T, doesn't necessarily mean time. It means whatever interval you're looking at. Well, we're looking at a 10-gram sample of chocolate. So I'm going to take that times 10. And notice the units are going to cancel, just like if you've taken a chemistry class. So basically, gram cancels with gram, and you're left with whatever 0.6 times 10 is, right? Which is 6. And look at what the units you'll be left with is insect fragments. So you would expect 6 insect fragments. But it says, compute the probability of getting exactly 3. Well, now you can see here, lambda is 0.6. Like I said, T is 10. Now you can see an illustration of the formula. So 0.6 times 10. So P of 3, and so the probability that you will get exactly 3 insect fragments, and those is equal to P of 3. And I'll just rewrite it so you can see it, 0.6, times 10, whole thing to the 3rd power. And you see here, over 3 factorial. But then notice, actually I want to illustrate that formula I was talking about earlier. Notice that P of x, the way remember how I said I like to think about it as mu to the x over x factorial e to the negative mu? Well, you see, like I said earlier, mu is equal to lambda t, which I had computed was, 0.6 times 10, which was 6 insect fragments. Well, notice that, mu is equal to lambda t. Notice that is that expression right there. Lambda t, see, so by substitution, I could view it like this, because we're going to see in the near future they're going to ask us for mu, the expected value, which would be 6 insect fragments in the 10 grams of chocolate. Okay? But anyhow, if you compute this out on your calculator, if you type it out, you're going to get 0.0892. Now, a lot of people don't know how to do that, so let's take a look. Now, notice, when we did binomial PDF and CDF, notice that if you go to the same menu, I'll show you where I went. Second distribution. Let's hit that again. Second distribution here in yellow, or second vars, you could say. Slide down. It's same place where the binomial distribution stuff was. Now we see Poisson. Aha. Now this is Poisson PDF, because it's not cumulative. You're looking at one discrete event. This first one here is a PDF, the probability that exactly 3 insect fragments. So let's key it in. Let's see how they get that 0.0892, just trying our calculator. So you have, so you would have your Poisson PDF, and then the way the calculator wants you to put it in is mu comma x. So we said the mean would be 6, the expected value would be 6, comma, and then x is the thing you're interested in observing, so the probability that you would actually get only 3 insect fragments. So, see, 0.0892. Or whether you crunch it out by hand using that formula, you're still going to get 0.0892. So we're showing you kind of both ways here. So let's see if I can highlight that. So Poisson PDF, if you're a TI-83 type person, or this way, either way you're going to get 0.0892. Okay? Now we play around with the other questions. Well, what's the probability that you would get less than 3 insect fragments in that 10 grams? Well, less than 3 in math, and here's where you got to be careful, translates to the probability that x is less than or equal to 2. See, less than 3 means 0, 1, or 2, basically. I like the way they wrote it here. Probability of 0, 1, or 2, added together. Well, I could do that by hand, or let's practice using that Poisson CDF now, which accumulates from the left. So, because you see the answer here is 0.0620. Right, now let's practice. second distribution. Let's go down to Poisson CDF, cumulative distribution function. Again, the mean is still 6, comma, what we're accumulating up to. So remember, the CDF is engineered to accumulate from 0 up to some stopping point, and this stopping point is 2 in this case. It's very similar to how we did the binomial distribution. See, 0.06196, or rounded 0.062, just like here. Very good. All right. Now let's practice this last one, and now this is a little tricky. Notice here we're looking at the probability that you would get greater than or equal to 3, or 3 or more insect fragments in that 10 grams. So 3 or more, I just want to translate here, 3 or more. Now we know the complement rule. We can just use the complement rule, and we have to, because it's going to be easier. So 3 or more, the opposite of that would be, 2 or less. So if we use the complement rule and just take 1 minus the probability of 2 or less, well, we had figured that out in the step above. Okay, so 0.938. So notice that you're often utilizing that complement rule, because you can't use the Poisson CDF function, is engineered to accumulate from 0 on up. So if I really wanted to get 3 or more, I'd just utilize that complement rule. All right, hope that helps. Okay, so objective 3 is find the mean and standard deviation of a Poisson random variable. So, oops, let me go back one. So as I mentioned before, mu is equal to lambda t, and standard deviation of the random variable x is basically equal to the square root of mu. So once you find mu, it's easy to find standard deviation. You just square root the mu. Okay, so a random variable x that follows a Poisson process with parameter lambda has a mean, or expected value, and standard deviation given by these formulas, where t is the length of the interval. Okay, Poisson probability distribution function. Like I said, I knew this was going to pop up. They're just telling us, now that we know the formula for mu, they're writing it in a different way, right? The formula for the probability. If x is the number of successes in an interval of fixed length, and x follows a Poisson process with mean mu, then by substitution, the probability distribution function for x is this, where, recall, earlier we looked at it as, lambda t, whole thing to the x over x factorial, and that's a lambda, times e to the negative lambda t. But now we know, I'm just going to change the color here, now we know that lambda t, everywhere we see a lambda t, we can replace that with the Greek letter mu. So it's like substitution. That's why I prefer the formula like this. Okay? So now we're back to that lovely insect problem. So the FDA, again, the FDAL level for insect filled in chocolate is 0.6 insect fragments per 1 gram. It says determine the mean number of insect fragments in a 5-gram sample of chocolate. So, and it also wants us to compute the standard deviation. So, here obviously I have it typed out, but I remind you that you always start by reminding yourself the formula, lambda t. Here, I don't like the units aren't written out, so your lambda is 0.6, I'm going to write here, IF, insect fragments per 1 gram. But you're looking at your t, your fixed interval, it's not time, but in this case it's grams of chocolate, is your 5 grams. I like to write the units because you can see grams canceling, and you can see what you're left with. So mu equals whatever 0.6 times 5 is, which is 3, but look at the units on that, IF. insect fragments. So we would expect 3 insect fragments. That's what we mean by expected value. Okay? We would expect 3 insect fragments in a 5-gram sample of chocolate. Okay? And likewise, we said that it'd be easy to find standard deviation then. It's just the square root of lambda t, which is basically the square root of mu. So whatever the square root of 3 is, which is basically a little over 1. All right. Just wanted to say that this is where we're going to hold it today. We will not be covering hypergeometric probability distribution function in this course, but perhaps in another course you'll see that. Good luck out there.